Next, we have the influence of urban pumping on groundwater quality. Peter Knappett is associate professor at the Department of Geology and Geophysics at Texas A&M University.
Thanks.
Welcome.
Thanks. Okay, so in the words of Monty Python, and now for something completely different. So this isn't our karst talk. This is a simpler system that I'm talking about. It's actually a coastal heterogeneous aquifer system, and instead of being in Texas, it's actually in Bangladesh. There's a conceptual model here that I'm starting out with, and it shows the basic problem, which I think is general to many groundwater-dependent cities around the world. What's special about Bangladesh and much of Southeast Asia is that in the shallow aquifers, there's widespread naturally occurring arsenic. So people often ask, when I talk about arsenic in Asia, they often ask, well, who put the arsenic there, or what industry put it there? But it's actually completely naturally occurring. It's called geogenic arsenic. And there's a system of aquitards, clay and silt layers that kind of divide a bunch of layered aquifers. And so far, the vast majority of the arsenic is confined in the first 30 meters or so of the aquifer, and it diminishes with depth. But as they pump aggressively from their megacities, examples are Delhi, India, or Dhaka, Bangladesh, or Hanoi, Vietnam, they're aggressively changing the hydraulic gradients, especially the vertical hydraulic gradients. And over time, that could lead to vertical migration of shallow groundwater into the deeper aquifers. And I believe in Texas that there's a similar processes could happen. I wanted to mention my talk is based on two papers that appeared last year in Journal of Hydrology and in Nature Communications with collaborators at Columbia University and University of Delaware. For those of you who don't think about Bangladesh every day, it's located close to India and just south of the Himalayas. The Ganges-Brahmaputra Delta is the largest delta in the world by volume. Okay, it actually beats the Amazon Delta or the Mississippi Delta in terms of volume. And one reason is there's two reasons for that. One reason is that it has two very large rivers come down, cut their way through the Himalayas and come down and bring a lot of sediment into the Bay of Bengal. The Bay of Bengal is located very close to one of the fastest growing mountain chains in the world, the Himalayas, and so there's a lot of fresh sediment being eroded off of these mountains, and at the same time, the Indian subcontinent is creating those mountains when it subducts underneath the Eurasian plate, and that's creating what's called accommodation or space for the sediment to be deposited. And so as a result, there's a lot of fresh sediment gets deposited on that delta. In terms of until about 1980, people in Bangladesh and much of India got their drinking water from surface water. And because sanitation was and still is very poor and population density is very high, there was a high rate of death, especially of children before the age of 5. So about 1 in 3 children died before the age of 5, largely from consuming surface water with fecal contamination. Over the course of about 15 years, from 1980 to 1995, the country went completely groundwater dependent. They went from drinking very little groundwater to drinking almost 100% groundwater. And in 15 years, virtually every family had one of these hand pump wells, or they call them tube wells, in their backyard. They're very affordable. They were about $100 US each, and there were about 10 million of them in existence in the mid-1990s. Unfortunately, also around the mid-1990s, they noted people showed up with skin lesions on their hands and high rates of intestinal cancers. And in a couple of years, they made the link very quickly between arsenic in the shallow aquifers and these high rates of cancer and other diseases that were coming out of the villages, people that were consuming them. So again, relating this back to Texas, Texas has got geogenic arsenic. It shows up pretty broadly in the Ogallala Aquifer system. There's also fluoride around Texas and selenium. And so these are this is part of the general topic of geogenic contaminants. So what they know is that it's naturally occurring, and it causes a long list of diseases over time. It causes chronic diseases similar to smoking. Okay, so you have a statistically higher chance of getting certain kinds of cancer if you're exposed to arsenic in your drinking water over time. As a result, a lot of people, just like smoking, a lot of people feel lucky, okay, and they don't necessarily feel a lot of pressure to get their well tested or to change their drinking water source. And so education plays a big role in mitigation. There's some mitigation options. Obviously, if we don't test the water, people can't avoid it. Okay, so everything starts with testing. Once the wells are tested, a lot of people choose to switch to a neighbor's well. We call this lateral switching, where because the distribution of arsenic is very heterogeneous in the shallow aquifer, they can switch very easily to another neighbor's well 50 meters away. It's nothing like Texas in terms of land ownership. You can go ahead and take your neighbor's water and nothing bad will happen to you. Another option is drilling deeper, and drilling deeper is an option. It has to be more of a coordinated option, and so these are community wells. And so again, this is something that might not. The closest analogy in Texas would be having a municipal well for a town, but in the villages, a community well will supply about 50 to 300 families, and they'll walk about 5 to 10 minutes to get their water. The deeper wells are more expensive. They're about $1,000 each to $2,000 each, and so no group of families can organize that money together. Instead, they wait for their government to come along and drill it, or for some NGO to put them in, and they'll wait for many years for that. At the same time, there's point-of-use filtration, which is not very successful in Bangladesh just because of lack of funding and know-how to keep it going. I mentioned that the arsenic distribution in the shallow aquifer is very heterogeneous and very difficult to predict. This is a data set of 6,000 wells that were tested in 2001 by a group at Columbia University, and the yellow indicates low arsenic and the red dots indicate high arsenic. And you can see that there's some villages like this one that are almost all high in arsenic, and other villages that are almost all low in arsenic. But in many cases, like this whole string of villages along the river, there's a lot of heterogeneity, and so there's a lot of wells. A low arsenic well can occur directly next to a high arsenic well. And this is one reason why arsenic is number 2 on the EPA's drinking water contaminant list, and it's one of the 3 top priority recommended contaminants to test for by the World Health Organization. And it's because it's very difficult to predict, and it occurs in a lot of different environments. So in this picture, you can see two major uses for groundwater in Bangladesh and in much of Asia. We have these megacities with 20 million people easily in them, and 20 million people consume a lot of groundwater for drinking. And in the foreground, there's rice irrigation, and rice requires a lot of water, especially to get multiple crops a year. It's the fastest growing city in the world. This slide's a little bit old, but now we're probably up around 17 million people. A quarter of them are homeless. It's very poor. And if we look at the pumping intensity in terms of cubic meters per square kilometer, it's about a million cubic meters per square kilometer averaged over the city. So what that means is that means about a standing. If you factor in porosity, then it's about a standing 2 meters of water. Think about how much water much of Houston is under right now, and that's about how much water Dhaka consumes annually. Then in comparison, the rural irrigation to grow rice across the countryside is about a standing 60 centimeters of water. But the difference is that this is highly focused on urban areas, whereas this is distributed across the entire country. I did a couple calculations, and I found that Bangladesh fits into Texas 5 times. And yet the population of Bangladesh is 8 times the population of Texas. So that gives you a little bit of an idea. It has about 180 million people living in a fifth of Texas. So really, human consumption of groundwater for growing food and for drinking is the major use. So 10 years ago, this was what the urban drawdown cone around Dhaka looked like. The actual city of Dhaka is just right in the middle here, but the cone of depression is extending outwards by it's about 70 kilometers across in this picture. This is the phreatic water table, and when you have this kind of layered system of aquifers and aquatards, there isn't such a sharp definition between phreatic water table and potentiometric surface of the confined aquifer, but the two are actually similar. But so across the country, the green basically means the water table is right near the surface. It's within the first 1 to 4 meters of the surface. So it's a very shallow water table, but below the city of Dhaka, the water, and 10 years ago, the water level had dropped 60 meters below surface, and today it's down to 80 or 90 meters below surface in some places. The black box here is our study area. So the study objectives were for this study are to, first of all, it's to assess the impact of Dhaka pumping on the surrounding rural population's access to low arsenic aquifers. The second objective is to assess the impact of Dhaka pumping on sort of the long-term sources and rates of recharge to the deep aquifer to figure out if that is going to impact, if there's going to be a long-term impairment of the deep aquifer water quality over time. The first hypothesis is that depressurization of the deep aquifer underlying Dhaka is limiting villagers' access to low arsenic aquifers. And the second hypothesis is that vertical recharge is accelerating within the expanding drawdown cone area, and this is increasing the likelihood of migration of the high arsenic water. So this is just a snapshot of our infrastructure that we use for this study. The boxes and the circles represent monitoring wells or community wells that we converted to monitoring wells without really disturbing them. And then there's this gray box here that represents the intensive study area where we did some modeling out on the fringe of the drawdown cone. This is a major river coming through here. This is called the Magna River. So that's it's a little bit like a boundary condition, but only if it's connected to the aquifer. During the first year of my postdoc at Columbia, I spent about 3 months in the field mapping, taking apart and mapping about 200 of these community wells. And this is a GPS receiver in the background where we did this fast-static GPS survey. In a delta, it's actually quite tricky to measure hydraulic gradients because there's no topography, and most of the lateral hydraulic gradients are 5 centimeters per kilometer, 10 centimeters per kilometer. So you have to have really accurate elevations of your monitoring wells to even detect which way the groundwater is flowing, let alone quantifying it. I want to, how do I, yes. There we go. So this is how about 90% of the wells are drilled this way in Bangladesh. It's a reverse, here's the scientific name. It's a reverse circulation percussion drilling method. It's also called the hand flapper method, where they're basically creating suction with the hand on top of the pipe, and then the lever is pulling the pipe up, and it's just sucking all of the silt and clay and sand up the well. And tens of millions of wells are drilled this way across deltas in Asia. It's very effective, and if you want to do a nice study, you can put in 10 or 20 monitoring wells for just a few $100s in a day. So when we look at the deep aquifer, the high potentiometric surface in the deep aquifer, it's declining west towards Dhaka. And this Rose diagram shows that actually when we kind of sum up which direction that hydraulic gradient's going, its point is declining due west every day of the year, basically. So even though there is a lot of seasonal fluctuations because it's a monsoonal climate, it doesn't really shift. And so this was the strongest indication we had that even though we're about 30 kilometers away from the center of Dhaka, we're still seeing a strong kind of dominant effect of the Dhaka pumping. So this was some of the early evidence we had that the Dhaka drawdown cone had arrived at this study site. One of the reasons why this is our study site, like why wouldn't we study Dhaka pumping in Dhaka? Well, one reason is because this area has been intensively studied for arsenic occurrence in groundwater and arsenic exposure to a population by an NIH-funded Arsenic Superfund program based at Columbia University for 20 years. This picture here shows the distribution of arsenic, kind of just a cross-section looking north through our intensive study area. All the small yellow dots represent arsenic concentrations, sorry, the small little dots. Blue represents arsenic that's safe, or groundwater that's totally safe, so it has less than 10 micrograms per liter of arsenic in it, which is the US EPA drinking water limit. Green represents anything between 10 and 50 micrograms per liter. 50 micrograms per liter is the old US EPA limit, which Bangladesh still uses. And then anything that's red is over 50 micrograms per liter, so quite dangerous. You can see that from this graph, you can see the distribution of where the wells tend to be installed. They tend to be in the first 10 to 50 meters. There's a few more wells that are installed around 50 to 70 meters, and those are still private wells that were installed with that hand flapper method. Okay, so they're still affordable for like a rich family to put in. But then we have a small number of very deep wells down here, and the very deep wells are practically all blue, as is the deeper private wells. And that indicates that the groundwater there is quite safe in terms of arsenic. The large circles here represent community wells that we had placed pressure transducers in. There's about 22 of them. And what we learned about the pressure transducers over multiple years is we learned a couple things. First of all, we learned that the water levels in the pressure transducers were declining over time, over multiple years. This is just the first 2 years of data. We have about 5 years of data now. We also learned that some of these wells, the ones that are colored kind of in hot colors, they show this is pumping noise. A lot of people in this room look at hydrographs coming from production wells all the time, and so this is what a community well hydrograph looks like hasn't been filtered for pumping noise. Well, we can see that the pumping noise stops in the dry season that year, and then the pumping noise stops again the next year, but it stops for longer. And actually, in each year, it stops longer and longer until the well was finally abandoned. And so that's this well right here. And what's happening is that as the Dhaka drawdown cone depressurizes this safe, drinking water aquifer, the suction pumps aren't able to access that water anymore because the water level drops below 9 meters below surface, which is the limit that suction pumps can suck water from. And so they have a kind of a technology problem now that they have to deal with. And given my experience with Bangladesh is it might take several years for them to start to adjust to this new normal, I guess. And in the meantime, during this time of the year when these wells are not working, you have hundreds of families that are drinking high arsenic water, because that's the closest wells they can get to. So, just stopped working. Okay. There's another video. There we go. All right, so this is looking north through the, and it's looking at water levels in the deep wells. So wells that are actually deeper than 150 meters. It says 120, but it's so it's the deep aquifer, and This is 1 year of data, and what I want you to see is this is the Magna River level that's actually very close to this regression line that's fit through about 15 deep community wells. And we're going into the monsoon season here, where the water level's up quite high. But if you watch the shape of watch the shape of the regression line, it shifts from totally straight to curved or quadratic. And there's an equation down here that's a best fit equation that's basically describing how quadratic that line is, okay? So if we just take a simple 1D flow model, and if we assume that this system is a 1D, if we model it with a 1D model and just use Darcy's law, if the hydraulic gradient is steeping over time, then we know that it must mean that there's more water coming into the system. And so that water, what I believe is happening, I think the water that's coming into the system is vertical recharge coming from above. And so we can tell basically instantaneous vertical recharge fluxes. We can calculate that from how bent that line is. So when the line is very straight, it means there's a constant flux of groundwater going from east to west. And when it's quadratic, we know that there's new water coming in because the hydraulic gradient is getting steeper and steeper as it goes from east to west. And I wanted to point out, this is a couple images from NASA. I just use them to emphasize how much flooding Bangladesh gets on a regular basis. In extreme years, the country is 2/3 underwater. But especially this region here, which is called the Sylhet Basin, you can see there's quite a bit of water here. This is in the early monsoon, just after probably a few rainstorm events. The Sylhet Basin is this depressed area that is the headwaters for the Meghna River, which flows right through our field site. If you fast forward about 2 months, there's a lot of cloud because it's the monsoon. You're probably not going to get a day without cloud during the monsoon, but you can see that the Sylhet Basin is basically one big lake. Okay, so people switch from riding bicycles to paddling boats during that time of year. So that's important to understand the response of the hydraulic heads over time. So what I think is so there's this interaction between pumping from Dhaka and these seasonal monsoonal fluctuations in the water table. So in the late dry season, in the early wet season, that regression line was quite straight. And when that regression line is straight, it means there's very little new recharge coming into the aquifer. But in the late wet season, when there's widespread flooding on the surface, and in the early dry season, the shape of that hydraulic, the shape of the potentiometric surface was very quadratic. It was so it was getting steeper and steeper as it went from east to west. And we can calculate that meant that there was a lot more vertical flux of a recharge coming into the aquifer. So this is a busy graph, but basically, if you just look at the blue line is quantifying vertical flux into the aquifer, into the deep aquifer over 2 years. And this is just showing that on average, it's about 0.22, so about 22 centimeters per year is the average Darcy flux. Okay, if we want to get velocity, then we just divide by porosity. So if your porosity is 50% or something like that, then you would get about 0.5 meter per year on average vertical flux. Now keep in mind that we're on the extreme eastern boundary of the Dhaka drought cone. It doesn't really say what's happening in the middle of the Dhaka drought cone or throughout the whole area, but this is where we had a lot of the arsenic data. To handle the regional modeling, there was quite a bit more sophisticated modeling that was done, where a student, Mahfouz Khan, working with Holly Michael at the University of Delaware, produced about 60 different models. One was a homogeneous model for the Dhaka, the region, and that's the flow pathways that are shown here. What he wanted to do is he wanted to calculate the residence times of water coming down from the surface under different heterogeneity scenarios. So he compared a homogeneous mod flow model here and this is one example of a heterogeneous model. But the problem always is when you want to model some kind of subsurface system is that we don't know the exact structure of the subsurface. And so what they did is they tried to deal with that by making 60 equally probable realizations of the silt and sand layers based on the geostatistical behavior of what they knew about the system. And then they calibrated a mod flow model for each of those 60 realizations, and then together those were called the ensemble. So the ensemble is the group of models for which any one of these scenarios are possible. And what they found is that in the homogeneous model, it took the fastest transport time from the surface down to the deep aquifer was 89 years. And so when you factor in retardation of arsenic, which can be anything from 10 to 20, it seems like it'll be hundreds of years before there could be a problem. But if you look at the ensemble, the behavior of the ensemble of models, the minimum transport time was down to only 7 years. And so that heterogeneity allowed certain recharge windows to open up and greatly shortened many of the flow paths, and resulting in this very likely scenario where in the next 10 to 40 years, we could have sort of hotspots of high arsenic popping up in the deep, even in the deep aquifer. In conclusion, the deep urban pumping combined with widespread natural arsenic contamination in the shallow aquifers has created this effectively drinking water scarcity in one of the wettest places on Earth. Continued increases in DACA pumping could do irreparable damage to intermediate and deep aquifers, with expected vertical movement of arsenic ranging from anything from 5 centimeters per year on the eastern fringe of the DACA drawdown cone to even tens of meters per year closer to the city center. And I want to acknowledge these people that I worked with. Thank you.